Every force you've ever experienced has a particle behind it. Electromagnetism has the photon. The nuclear forces have their carriers too. All confirmed. All found. Gravity has nothing. We've built the most sensitive instruments in human history. We've split atoms, mapped the early universe, detected ripples in space-time itself, and the particle that supposedly carries gravity has never been seen. Ever. Today we go after the graviton. What the math says it must be, why detecting even one is beyond any technology that could physically exist, and what its absence might be telling us about the deepest structure of reality. If you enjoy this journey, subscribing means you won't miss where it leads. Prepare yourselves. We begin. There is a rule that governs every interaction in the universe, every push, every pull, every collision. At the deepest level, all of it happens because particles are exchanging something, tiny invisible messengers flying back and forth, carrying the force between them. That is how physics actually works beneath the surface. And for almost every force we know, we have found those messengers. Almost. Start with something you already know. Light. When you switch on a lamp, photons pour out of the bulb and travel across the room until they hit your eyes. That much most people know. But photons do something else too. They carry the electromagnetic force. When two electrons push each other apart, they do it by exchanging photons. Not the visible kind you can see, but virtual photons, flickers of energy that exist just long enough to transfer a kick between two charged particles. The repulsion you feel when you push two magnets together, that is a storm of virtual photons happening between your fingers. Physicists call these force carriers gauge bosons. For the electromagnetic force, the gauge boson is the photon. For the weak nuclear force, the carriers are the W and Z bosons, discovered in 1983 at a particle accelerator in Switzerland. For the strong nuclear force, the carriers are gluons, confirmed experimentally in 1979. 3 forces, 3 sets of messenger particles, all found, all measured, all integrated into one of the most precise theories in all of science, the standard model of particle physics. Then there is gravity. Gravity is everywhere. You feel it right now pressing you into your seat. It holds the atmosphere around the planet. It keeps the moon in its path and steers galaxies across distances so vast that light takes millions of years to cross them. Gravity is the most obvious force in the universe, and we have no confirmed messenger particle for it. None. The graviton, the theoretical carrier of gravity, has never been detected. Here is what makes that strange. Gravity behaves like it should have a carrier. It radiates outward from mass in all directions, weakening with distance in exactly the same mathematical pattern as other forces. Gravitational waves travel at the same speed as light. All of this fits the profile of a force that has a particle behind it. The math strongly suggests the graviton exists, but suggestion and proof are separated by a gap so wide that, as you'll soon see, crossing it may be physically impossible. Before we even get to the detection problem, we need to understand what the graviton is supposed to be. And to do that, we have to understand something that physics discovered quietly over the last century. Forces are not things that reach across space. They are things that happen between particles when messengers are exchanged. That shift in perspective changed everything. The question that drove physicists toward the graviton was simple. If electromagnetism is carried by photons, and the nuclear forces have their carriers, then gravity must have one too. The universe seemed to demand consistency. Every force plays by the same rules. So physicists sat down and asked, what would gravity's messenger look like? The answer they found was stranger than anyone expected, and it created a problem so deep that more than a century of brilliant minds has failed to fully solve it. Picture 2 ice skaters standing on a frozen lake, facing each other. One of them throws a heavy ball to the other. The moment the ball leaves the first skater's hands, they get pushed backward. The moment it reaches the second skater and they catch it, they get pushed backward too. Neither skater touched the other, but both of them moved apart. A force passed between them through an exchange. That image is a rough but genuinely useful way to picture what happens when 2 charged particles repel each other. They exchange a virtual photon. The exchange pushes them apart. The photon is the ball. The skaters are the particles. The repulsion is the result. Now, Here is where it gets more precise. In quantum mechanics, particles are also waves. They have fields spreading around them, fields that carry energy and information. When a particle wants to exert a force on another particle, it disturbs its own field. That disturbance travels outward. When it reaches another particle, it disturbs that particle. An interaction happens. We call the quantized ripple of that field the force-carrying particle, the gauge boson. This framework is called quantum field theory, and it is the most thoroughly tested idea in the history of science. Every particle we know of is actually a ripple in a corresponding field that fills all of space. The electron is a ripple in the electromagnetic field. The photon is a ripple in the electromagnetic field. The Higgs boson, discovered in 2012, is a ripple in the Higgs field. Fields are the primary reality. Particles are what fields do when they get excited enough. The Standard Model takes this logic and runs with it. It builds the electromagnetic force, the weak nuclear force, and the strong nuclear force all out of this same idea. Fields that have quantized ripples, ripples that carry forces. The whole structure is mathematically elegant, internally consistent, and experimentally verified to a precision that makes it the most accurate theory humans have ever constructed. Predictions from the Standard Model have been confirmed to more decimal places than any other theory in any field of knowledge. Gravity is outside it entirely. When physicists try to add gravity to the Standard Model using the same framework, find the field, quantize it, name the ripple, the math breaks down. Explodes, really. You get answers that are infinite where they should be finite. The very language of the Standard Model seems to reject gravity as a member. That breakdown has a name and a reason. But before we get there, we need to understand what the graviton's predicted properties tell us about why gravity is so uniquely difficult. Because the graviton is not just another gauge boson with a different name. Its required properties are unlike anything else in the Standard Model. One property in particular makes it structurally different from every other force carrier. And that property is the key to understanding why gravity refuses to fit. The graviton's spin is set not by experimental measurement, but by the logic of what gravity does. And that number, that single mathematical property, carries consequences that reach all the way down into the geometry of space-time itself. The photon does two jobs simultaneously, and most people only know about one of them. The first job is familiar. Photons carry light. Every color you have ever seen arrived at your eyes as a stream of photons, each one carrying a precise packet of energy. The energy of a photon determines its color. Low-energy photons are red, high-energy photons are violet, and the ones beyond either end of that range are invisible to human eyes but still physically real. Radio waves are very low-energy photons. X-rays are very high-energy ones. The full range is called the electromagnetic spectrum, and it is all the same particle at different energy levels. But the photon's second job is the one that matters most for understanding the graviton. Photons carry the electromagnetic force. Here is how that works. Every charged particle, an electron, a proton, anything with electric charge, is surrounded by an electromagnetic field. That field is not a metaphor. It is a real physical thing, spread through space, storing energy, responding to disturbances. When a charged particle accelerates or interacts with another charged particle, it creates a ripple in its electromagnetic field. That ripple, quantized, is a photon. The photon travels from one particle to another, is absorbed, and transfers momentum. The result is what we call a force, attraction or repulsion, depending on the charges involved. Virtual photons, the ones doing this force-carrying work, are slightly different from the photons you see with your eyes. They exist only in the gap between interactions. They carry momentum and energy, but they do not travel freely through space to be detected. They are, in a precise mathematical sense, borrowed from uncertainty. Quantum mechanics permits their brief existence as long as they disappear before the universe's accounting demands they be real. The technical name for this borrowing is the Heisenberg uncertainty principle, applied to energy and time. What makes the photon a clean, well-behaved force carrier is its spin. Quantum spin is an intrinsic property of particles, like mass or charge. Photons have a spin of 1. That single number determines how the photon interacts, what fields it can couple to, and what kind of force it produces. A spin 1 particle couples to things that have direction: charge, current, flow. Electromagnetism is a directional force. It pushes charges along specific lines of electric and magnetic field. The spin of the carrier matches the geometry of the force. The weak and strong forces also have spin 1 carriers. All three of these forces fit neatly into a mathematical structure called gauge theory. Gauge theory is built around symmetry, the idea that physics looks the same even when you rotate your mathematical description in certain abstract ways. Spin 1 carriers are the natural result of that symmetry. They are what gauge theories produce. When physicists asked what kind of carrier gravity needs, they went to the same logic. What is gravity's geometry? Gravity does something the other forces don't. It couples to energy and momentum in all directions simultaneously. It responds to mass, pressure, flow, stress, everything that carries energy everywhere at once. Matching a carrier particle to that geometry requires something with a higher spin, specifically spin 2. And a spin 2 particle is a creature so strange that just hearing what it implies about space should give you pause. Because a spin 2 particle does something to the fabric of reality that no other particle does. Spin, in quantum mechanics, is a number that tells you how a particle transforms when you rotate it. A spin 1 particle, like the photon, looks the same after a full 360-degree rotation. That sounds obvious. Everything should look the same after a full rotation. But in quantum mechanics, it gets stranger. A spin 1/2 particle, like an electron, needs 2 full rotations to return to its original state. One rotation of 360 degrees is not enough. The electron comes back looking different after one rotation and only returns to itself after 720 degrees. If that sounds impossible to visualize, that is because it involves properties of quantum objects that have no real equivalent in everyday experience. Mathematically, it is precise and measurable. Physically, it is deeply strange. Now here is the thing about the graviton. The predicted spin of the graviton is 2. A spin 2 particle only needs half a rotation, 180 degrees, to look the same as it started. That means if you rotate the entire interaction by half a turn, the graviton is unchanged. Think about what kind of force behaves that way. A force that looks the same from 2 opposite directions. A force that is symmetric under half rotation. That is exactly what gravity does. No matter which direction mass points, gravity pulls toward it equally. The force is the same from every angle you approach it. The spin 2 nature of the graviton is forced on us by the geometry of gravity itself. But spin 2 creates a problem that has no equivalent in the rest of particle physics. When physicists built quantum field theories for spin 1 particles, the math had a special property that kept answers finite. Infinities appeared in calculations, but a process called renormalization allowed physicists to absorb them into measured quantities like mass and charge. The infinities were real, but controllable, tamed. The resulting theories, quantum electrodynamics, the theory of the weak force, quantum chromodynamics for the strong force, became precise machines for calculating probabilities to extraordinary accuracy. A spin 2 field generates a different kind of infinity. The infinities it produces grow worse with each calculation, not better. Every time you try to correct for an infinity, a new and larger one appears. The process that saves spin 1 theories fails completely for spin 2. This is the mathematical signature that tells physicists the theory is incomplete, that something deeper is missing. It is the first wall physicists slam into when they try to make gravity quantum, and it raises a question that goes to the foundation of physics. Why is gravity, alone among all the forces, described by a spin 2 carrier? Why does this one geometrical difference make the math so catastrophically harder? One reason is that the graviton, unlike every other force carrier, couples to itself. Photons carry the electromagnetic force, but carry no electric charge. They do not interact with each other directly. The graviton carries the gravitational force and carries energy. Energy gravitates. So gravitons must gravitate toward each other. They interact with themselves. That self-coupling adds layers of complexity that the other forces simply do not have. A graviton is not just a messenger. It is a messenger that is also subject to the very message it carries. That self-reference is beautiful and maddening in equal measure, and it is only the beginning of what makes the graviton unlike anything else in physics. The standard model of particle physics is by any reasonable measure humanity's most successful scientific theory. It describes 12 fundamental matter particles, 6 quarks and 6 leptons, and 4 force-carrying bosons, the photon, the W and Z bosons, and the gluon. It predicts the magnetic strength of the electron to 11 decimal places of accuracy. 11 decimal places. That is the equivalent of measuring the distance from New York to Los Angeles and being accurate to within the width of a human hair. And gravity is nowhere in it. This is not a small omission. Gravity is the force that shapes the large-scale structure of the entire universe. It governs the formation of galaxies, the lives of stars, the paths of planets, the expansion of space itself. It is the most cosmically dominant force by a vast margin, and the most precisely tested theoretical framework in science simply has nothing to say about it. The reason is structural. The standard model is built on quantum field theory, which assumes that space-time, the stage on which particles move and interact, is flat, fixed, and smooth. Quantum field theory treats space and time as a background, a given, a container that holds physics but does not participate in it. General relativity, Einstein's theory of gravity, does the opposite. It says space-time is not a background at all. Space-time is a dynamic, flexible structure. Mass and energy warp it. Curvature of space-time is gravity. The stage itself is a character in the story, bending and stretching in response to everything on it. These two frameworks start from opposite assumptions. Quantum field theory says space-time is fixed. General relativity says space-time is flexible. Trying to combine them is like trying to write a story where the characters change the rules of grammar as they speak. The two languages are incompatible at a deep structural level. When physicists try to force the two together, to quantize gravity the same way they quantize electromagnetism, the math produces answers of infinite magnitude for quantities that should be finite, probabilities greater than 100%, energies of infinite size. None of these answers correspond to anything physical. The calculation has broken. This breakdown does not mean gravity cannot be quantized. It means the naive approach of applying quantum field theory directly to general relativity fails. Something new is required, something that either reconciles the two frameworks at a deeper level or replaces both of them with a more fundamental description. The graviton sits in the middle of this crisis. If it exists, it is the bridge between gravity and quantum mechanics. Its discovery would prove that gravity can be treated like the other forces. Its absence, or the inability to ever detect it, might be telling us something more radical, that gravity works differently, that the graviton framework is an approximation, or that space-time itself is not a fundamental ingredient of reality. Every other force in the standard model has a known, detected carrier. Gravity's carrier remains a theoretical necessity, backed by powerful mathematical arguments and zero direct evidence. That asymmetry is one of the most important unsolved problems in all of physics. And it gets stranger when you ask exactly why. Despite the mathematical certainty that the graviton should exist, detecting even a single one appears to be flatly physically impossible. On September 14, 2015, two black holes that had been circling each other for billions of years finally collided. Each one carried a mass roughly 30 times greater than our star. In the final fraction of a second before they merged, they released more energy than all the stars in the observable universe combined emit in that same moment. That energy did not travel as light. It traveled as a ripple in the fabric of space-time itself, a gravitational wave. A detector in the United States, a pair of 4-kilometer-long tunnels arranged in an L shape in Louisiana, felt that wave arrive. The stretching and squeezing of space it caused was smaller than 1/10,000th the diameter of a proton. Yet the instrument caught it. The detection, made by the Laser Interferometer Gravitational Wave Observatory, which scientists call LIGO, was one of the most precise measurements in human history. Why does this matter for the graviton? Gravitational waves are, by every theoretical expectation, made of gravitons, just as light waves are made of photons. The wave that reached the detector in 2015 carried information encoded in gravitons that had traveled over 1 billion light-years. In that sense, the detection was indirect evidence that gravitons, or something playing the role of gravitons, are real. But indirect is doing a lot of work in that sentence. The detector registered a wave. A wave is a collective phenomenon. Billions upon billions of gravitons, all lined up, all acting together, produce a wave pattern that is large enough for a 4-kilometer instrument to detect. That is the key problem. LIGO can see the crowd, but not the individual. Detecting one graviton in isolation requires something that does not exist and, by current physics, cannot exist. Here is the thought experiment that makes this concrete. To detect a single graviton, an instrument would need to absorb that graviton and register a change. The change a single graviton produces is so tiny that the detector itself would need to be so massive and so cold that it would collapse into a black hole before it could function. A team of physicists worked through the numbers and showed that a graviton detector operating at or near the fundamental quantum limit, the most sensitive device the laws of physics allow, would need to be roughly as large as the planet Jupiter and cooled to temperatures colder than deep space. And even then, it would detect perhaps one graviton every 10 years. That calculation is confirmed physics. The impossibility of graviton detection is not a technological limitation we will eventually overcome with better engineering. It appears to be written into the structure of the universe. This raises a question that has no comfortable answer. If we can never detect the graviton directly, can we ever prove gravity is quantum? Can a theory remain scientific if one of its central predictions is untestable in principle? Those questions push us toward the deepest problem in all of physics. Not just what the graviton is, but why gravity is so extraordinarily, almost impossibly, weak compared to everything else. Hold a paperclip flat on a table. Now bring a small refrigerator magnet close to it. The paperclip jumps up. A magnet you can buy for $1, sitting in your hand, just overpowered the gravitational pull of the entire planet Earth. That is the hierarchy problem in its simplest form. Gravity is the weakest force in the universe by a margin so extreme it defies ordinary intuition. The electromagnetic force is roughly 10 to the power of 36 times stronger than gravity. Write that out, and it is a 1 followed by 36 zeros. The strong nuclear force is even stronger than that. Gravity is so weak that a single proton, sitting on a table, is pulled toward the Earth with a force so small it would take more atoms than exist in the observable universe, all pulling together to lift a single grain of sand. This weakness is not an accident of the way we built our units of measurement. It is a real, deep, structural fact about the universe, and nobody knows why. In the Standard Model, the strengths of forces are related to the masses of their carrier particles. Heavier carriers produce shorter range, weaker forces. The W and Z bosons are heavy, and the weak force is short range. The photon has no mass, so electromagnetism has infinite range. By this logic, the graviton should also be massless. Gravity has infinite range. But mass of the carrier does not explain the overall strength of the coupling. Something sets the strength at which gravity attaches to matter, and that something is an open problem. The hierarchy problem goes deeper than just the weakness. In quantum field theory, particle masses and coupling strengths receive corrections from virtual particles popping in and out of existence at every energy scale. For every other force, these corrections can be made consistent. For the Higgs boson, they require an extraordinary fine-tuning. The various corrections cancel each other to 1 part in 10 to the power of 32, and physicists find that fine-tuning disturbing. For gravity, the corrections are even worse. The natural energy scale of quantum gravity is the Planck scale, which is roughly 10 to the power of 19 times the energy of a proton. Gravity's weakness means the Planck scale sits so far above the scale of ordinary physics that bridging them mathematically requires a degree of fine-tuning that seems almost conspiratorial. Some physicists think the hierarchy problem is telling us something real about the structure of the universe. One leading idea is that gravity is so weak because it is the only force that leaks into extra dimensions of space. If space has dimensions beyond the 3 we experience, dimensions too small to detect directly, gravity could be spreading its influence across all of them, while the other forces remain confined to our 3-dimensional slice. What we measure as weak gravity might be the tiny fraction that stays in our dimensions. That idea, radical as it sounds, is a serious and active area of research. It changes what the graviton is. In extra-dimensional models, the graviton we would detect in our 3 dimensions is only a shadow of the full, higher-dimensional graviton. The full one might be just as strong as the other forces. We just cannot reach it. And if that is true, it means the graviton's weakness is a clue pointing to hidden dimensions of space that we have not yet found. The graviton in the standard picture has exactly 0 mass. No mass, infinite range, instant transmission of gravitational effects across the cosmos. This is confirmed indirectly. We observe gravity operating across billions of light years, with no sign of it weakening faster than expected. And a massive graviton would cause detectable deviations from that behavior. But what if the graviton had even a tiny mass? The smallest imaginable mass. A number so close to 0 it would take precision beyond anything we can currently measure to detect. The answer changes everything, and not in a small way. A massive graviton would move slightly slower than light. Gravitational waves would arrive at a detector after the light from the same event, a delay that grows larger over greater distances. The 2017 detection of merging neutron stars, observed simultaneously in gravitational waves and in light, set an upper limit on any graviton mass. If it exists, it must be less than 1/10,000 trillionth of the mass of an electron, a number almost indistinguishable from 0, but still conceivably above 0. The theoretical implications of even that tiny mass are enormous. A theory with a massive graviton is called massive gravity. Physicists spent decades trying to construct a version of massive gravity that does not produce absurd predictions. For a long time they failed. Early versions of massive gravity predicted that light bending around massive objects would be wrong by a factor of 3/4 compared to what general relativity and observation both show. That is called the Van Dam-Beltman-Zakharov discontinuity, a technical name for a serious physical problem. Even an infinitesimally small graviton mass seemed to produce a theory dramatically different from standard gravity. A theoretical resolution emerged decades later. A mechanism called the Weinstein screening showed that in regions of strong gravity, a massive graviton theory can recover the predictions of ordinary general relativity. The extra mode of a massive graviton, the extra degree of freedom its mass introduces, gets suppressed in strong field regions. Around a star, inside a solar system, in any region where gravity is significant, the theory heals itself. Far from masses, in the nearly empty stretches between galaxy clusters, the extra mode could resurface and produce detectable effects. Specifically, a massive graviton might explain what astronomers call dark energy. The accelerating expansion of the universe, observed since the late 1990s, is usually attributed to a cosmological constant, an energy density built into the fabric of space itself. A massive graviton changes the long-range behavior of gravity in ways that could produce the same observed acceleration without needing to invoke dark energy as a separate ingredient. The graviton's mass would cause gravity to behave differently at the largest cosmic scales, turning a repulsive effect on the expansion of space. So a graviton with mass could simultaneously threaten our understanding of gravity at solar system scales and explain the larger structure of the universe. Researchers actively test this using precision measurements of the solar system's gravitational behavior and large-scale surveys of galaxy distribution. Every measurement so far is consistent with 0 mass. But consistent with 0 is not the same as proven 0. The window remains open, barely, for a graviton with mass so small it hides just beneath our current ability to see. Einstein published his general theory of relativity in 1915. Within a decade, quantum mechanics had become a complete framework for describing atoms and particles. For 100 years, both theories have been tested relentlessly. Both have passed every test, and they are deeply, structurally incompatible with each other. Understanding why they clash is the key to understanding why the graviton is so hard to place. General relativity describes gravity as geometry. Mass and energy do not pull on each other through a force. They curve the space-time around them, and other objects follow the straightest possible paths through that curved geometry. A planet does not orbit a star because something tugs on it. It moves in a straight line through curved spacetime, and that straight line in curved geometry is a curve in our everyday experience. Everything falls freely. There is no force. There is only geometry. In general relativity, space-time is continuous and smooth at every scale. It can curve, stretch, and compress, but it is always a single unbroken fabric. The equations of general relativity treat space-time as infinitely divisible, with no smallest unit of distance or time. Quantum mechanics starts from a different premise entirely. Everything at the subatomic scale is discrete and probabilistic. Energy comes in chunks, called quanta. Particles do not have exact positions and momenta simultaneously. The Heisenberg uncertainty principle makes that impossible. At the quantum level, reality is inherently fuzzy. Values do not exist until they are measured. Here is where the incompatibility cuts deepest. In quantum mechanics, the uncertainty principle applies to energy over time. For a sufficiently short time interval, the energy of a region can fluctuate by a large amount. A vacuum is never truly empty, because energy fluctuations constantly produce pairs of virtual particles that appear and annihilate. The shorter the time scale, the larger the fluctuation allowed. Now, apply this to spacetime. If spacetime is subject to quantum mechanics, then at the smallest scales, the geometry of spacetime itself must fluctuate. Spacetime cannot be smooth at the Planck scale, the scale where quantum gravity must operate. The smooth, continuous manifold of general relativity should dissolve into a seething, foamy chaos of geometry fluctuating wildly in all directions. General relativity cannot tolerate this. Its equations require a smooth background to function. Feed them a foamy, fluctuating spacetime, and the equations lose meaning. The concept of a well-defined path through spacetime, the core of general relativity, ceases to exist. So we have two theories, each perfect in its domain, each unable to tolerate what the other requires at their shared boundary. That boundary is the Planck scale, the scale of distance and energy, where quantum gravitational effects become unavoidable. At the Planck scale, you cannot ignore either theory. And at the Planck scale, both theories break down simultaneously. Every candidate for a graviton lives in this contested territory. A graviton is the quantum of space-time geometry, the discrete particle-like ripple in the gravitational field. For it to exist in the quantum sense, space-time must be quantizable. For space-time to be quantizable, it must have some discrete, particle-like structure at its base. Whether space-time actually has that structure is one of the deepest open questions in science. And the answer, when we eventually find it, will determine whether the graviton is a real particle or a useful approximation to something far stranger. The natural thing to do, after quantum mechanics proved its power in the 1920s and 30s, was to apply the same methods to gravity. Physicists had successfully quantized the electromagnetic field to produce quantum electrodynamics. They expected, reasonably, that the same approach would work for gravity. It did not. The process of quantization starts with a classical field theory, Maxwell's equations for electromagnetism, for example, and promotes it to a quantum theory by treating the field as an operator that creates and destroys particles. For electromagnetism, this produces a well-defined theory with a clear particle, the photon, and a clear set of rules for how photons interact with charged particles. Applying this to general relativity means treating the gravitational field, or more precisely, the metric tensor, the mathematical object that encodes the shape of spacetime, as a quantum field. Ripples in that field are gravitons. On paper, the approach produces a theory. The graviton emerges as a massless spin-2 particle, exactly as expected. The theory even gives the right answers for simple gravitational interactions. Two particles exchanging a graviton and feeling a force is reproduced correctly. For those calculations, the approach works. The problem emerges when you try to calculate higher-order corrections. In quantum field theory, particles interact not just by exchanging a single carrier, but by exchanging multiple carriers, with loops of virtual particles contributing additional effects. These loop corrections are essential for accurate predictions. They are what makes quantum electrodynamics so precise. Computing them requires adding up contributions from particles at all energy scales, from low energies up to arbitrarily high energies. For electromagnetism, these sums produce infinities, but the infinities appear in a structured way. They can each be absorbed into a small number of physical quantities, the mass and charge of the electron, that are then fixed by experiment. After that procedure, called renormalization, the infinities disappear and the theory makes finite testable predictions. Renormalization works because the theory has only a finite number of parameters that need to be fixed. For quantum gravity, renormalization fails. Every loop calculation introduces new infinities. Each infinity requires a new parameter to absorb it. As you go to higher orders of calculation, you need more and more new parameters. The theory has an infinite number of free parameters, which means it has infinite freedom to be adjusted. A theory with infinite adjustable parameters predicts nothing. It is consistent with any possible experimental outcome, which means it is consistent with no experimental outcome in particular. This failure is not a technical problem waiting for a smarter mathematician. It is a structural signal. It says that naive quantum general relativity is what physicists call non-renormalizable. The theory is an approximation that works at low energies, but loses all predictive power as you approach the Planck scale. Something else must take over at high energies. A more complete theory that reduces to general relativity at large scales, but behaves differently and finitely at small ones. Finding that more complete theory is the central challenge of theoretical physics. Two serious candidates have emerged. They approach the problem from completely different directions, and they produce completely different pictures of what the graviton is and whether it exists at all. In the 1970s, physicists exploring a branch of mathematics called string theory made a discovery they did not expect. String theory had originally been proposed as a description of the strong nuclear force, and it had not worked well for that purpose. But when theorists examined the spectrum of particles that the theory naturally produced, the list of vibration modes that strings could take, they found something that had not been put in by hand: a massless spin 2 particle. No force, no fine-tuning, no adjustable parameter, just the mathematics of vibrating strings, taken seriously, producing a particle with exactly the properties the graviton must have. The spin 2 result is the mathematical fingerprint of the graviton. Its appearance in string theory was so surprising and so precise that many physicists took it as the first serious evidence that string theory was onto something real. Here is the core idea of string theory. Every particle in nature, electrons, quarks, photons, everything, is actually a tiny, one-dimensional loop or strand of energy, vibrating at a specific frequency. The particle you observe is determined by the pattern of vibration. A string vibrating one way is an electron. Vibrating another way, it is a photon. The theory has a single fundamental object, the string, and the diversity of particles emerges from its different modes of oscillation. Among those modes, string theory always produces a mode corresponding to a massless spin 2 particle. Always. It is built into the mathematics, and a massless spin 2 particle coupled to energy is by a theorem due to physicists Steven Weinberg and Edward Witten, necessarily the graviton. String theory does not assume gravity, it derives it. And the infinities? They disappear. The reason is that strings have a finite size, typically set by a length close to the Planck scale. In quantum field theory, the infinities arise because point particles interact at exact locations, zero-dimensional points, and the integral's overall energy scales blow up. Strings spread the interactions over a small but finite area. That spreading regulates the integrals. The infinities that plague quantum general relativity are smoothed away by the extended nature of the string. String theory produces a finite theory of quantum gravity. For many physicists, this is its most compelling feature. Whatever its other challenges, and there are significant ones, it offers a mathematically consistent framework in which a graviton exists and gravity is quantum mechanical. The challenges are real, though. String theory requires extra dimensions of space beyond the 3 we observe, typically 6 or 7 extra dimensions, curled up at scales too small to detect directly. It also predicts a vast landscape of possible universes, each with different physical constants, and has so far produced no unique prediction that could be tested and potentially falsified by current experiments. But the graviton in string theory is not a hypothetical. It is the theory's central prediction. the one that turned string theory from a failed theory of the strong force into the leading candidate for a theory of everything. Every string theory contains gravity. Remove gravity and you do not get string theory without gravity. You get a mathematical inconsistency. That is either a profound sign of the theory's correctness or a very elegant trap. And there is a completely different approach to quantum gravity that does not need strings at all. String theory asks, what are particles made of? Loop quantum gravity asks a different question entirely. What is space made of? The two questions lead to different theories, different gravitons, and a different picture of reality at the smallest scales. Loop quantum gravity, developed primarily in the 1980s and 90s by physicists Abhay Ashtekar, Lee Smolin, and Carlo Rovelli, begins with a simple but radical premise. If quantum mechanics applies to everything, and all evidence says it does, then it must apply to space-time itself. The geometry of space must be quantized. Space must come in discrete chunks. There must be a smallest possible volume, a smallest possible area, below which the concept of space loses meaning. These chunks of space are called spin networks, and the theory predicts that area and volume are quantized in units close to the Planck scale. The smallest possible area in loop quantum gravity is roughly 10 to the power of negative 70 square meters. Below that scale, asking what the geometry looks like is like asking what is north of the North Pole. The question has no answer. What does this mean for the graviton? In loop quantum gravity, the graviton is an emergent phenomenon. Space at the Planck scale is a network of interconnected nodes, each node representing a quantum of volume, each connection representing a quantum of area. The geometry of this network is the physics of gravity. Space-time, as we experience it, smooth, continuous, three-dimensional, emerges from the collective behavior of this network at large scales, the same way temperature emerges from the average motion of atoms. No single atom has a temperature. Temperature is a property of the crowd. Similarly, no single node in the spin network has geometry. Geometry is what the crowd of nodes looks like from far away. In this picture, the graviton is not a fundamental particle. It is a ripple propagating across the spin network, a wave in the collective behavior of quantized space. The graviton we would detect in a laboratory, if we could detect it, would be a long wavelength, low-energy ripple in a network operating at the Planck scale, a shadow of the true underlying structure. Loop quantum gravity is mathematically consistent in a way that naive quantum general relativity is not. It avoids the infinities of the perturbative approach by treating the geometry of space as the primary variable, not small fluctuations on top of a flat background. It makes specific predictions about the structure of space-time at the Planck scale, including the discreteness of area and volume, and it predicts that gravitational waves would travel at speeds that depend very slightly on their energy, an effect called graviton dispersion, which could in principle be tested by observing gravitational waves from extremely distant events. The Fermi Gamma Ray Space Telescope has searched for photon energy dependence in gamma ray bursts as a test of Planck scale physics. So far, the results are consistent with no dispersion, a result that puts pressure on some versions of loop quantum gravity without ruling it out entirely. Both string theory and loop quantum gravity predict a graviton, but they disagree on what it fundamentally is. And that disagreement reflects a deeper question about what reality is made of at its most basic level. Here is a thought experiment that exposes the core problem of quantum gravity in the most direct way possible. Take two gravitons, aim them at each other, let them collide. In any normal particle physics experiment, you fire particles at each other and calculate the probability of various outcomes. An electron hits a positron, a quark hits an antiquark. The calculation uses a precise set of rules from the standard model, and the result is a number between 0 and 1, a probability, always finite, always meaningful. Repeat this for gravitons, and the math collapses. As you increase the energy of the collision, the probability of certain outcomes grows. Keep increasing the energy, and the probability reaches 1, certainty. Push the energy higher still, and the calculated probability exceeds 1. A probability greater than 1 has no physical meaning. You cannot be more than certain that something happens. The calculation has broken, and it has broken in a way that signals the theory it came from is incomplete. This is called a unitarity violation. Unitarity is the principle that probabilities must always add up to exactly 1. Something must happen, and the sum of all possible outcomes must equal certainty. When a theory violates unitarity, it has stopped describing reality and started producing nonsense. In quantum electrodynamics, the theory that describes how electrons interact with photons, unitarity is preserved at all energies by a mechanism called gauge symmetry. The spin-1 nature of the photon and the mathematical structure it implies keeps probabilities below 1 no matter how high the energy goes. That protection is exactly what spin-2 gravitons lack. For graviton-graviton scattering, the probability of something happening grows with the square of the collision energy. At energies far below the Planck scale, the probability is small, and the theory is reliable. As you approach the Planck scale, the probability approaches 1. At the Planck scale, the theory breaks. This breakdown is not a surprise. Physicists expected it. The Planck scale is, by definition, the energy at which quantum gravity effects become dominant. The scale where our current theories must fail, and something new must take over. The graviton-graviton scattering calculation is simply showing you that boundary from the inside. It is the theory pointing at its own edge and saying, something else lives beyond here. What lives beyond the Planck scale in graviton-graviton scattering? At those energies, the collision would produce objects more extreme than anything else in physics. The energy concentrated in so small a space would, by general relativity, curve space-time enough to form a micro-black hole. The two gravitons would not simply scatter off each other. They would collapse into a tiny black hole, which would then evaporate by Hawking radiation. Black holes as the output of particle collisions. Black hole evaporation as the final state. That is what quantum gravity predicts at the highest energies. The graviton, in this picture, is the bridge between particle physics and black hole physics, and the bridge leads somewhere we have not yet mapped. On August 17, 2017, 2 neutron stars, each one a sphere of dense nuclear matter roughly 12 miles across, each containing more mass than our star, spiraled into each other after circling for hundreds of millions of years. The collision was catastrophic. It released energy in light, in gamma rays, in X-rays, and in gravitational waves simultaneously. Observatories on Earth detected the gravitational waves first. Approximately 1.7 seconds later, a gamma ray burst arrived from the same location. The gravitational wave signal and the light signal had traveled roughly 130 million light-years. Both arrived within seconds of each other. That 1.7-second gap corresponds to a difference in speed of less than 1 part in 10 to the 15th. Essentially, 0. The graviton, if it is the carrier of gravitational waves, travels at the speed of light to a precision that no previous test of any kind had approached. This result carries major implications. A massless particle always travels at the speed of light. Any particle with mass travels slower than light, and the heavier the particle, the slower it goes. The near-identical arrival times of the gravitational wave and the gamma rays set one of the tightest upper limits ever measured on the mass of the graviton. It also eliminated a large class of modified gravity theories, theoretical alternatives to general relativity that predict gravitational waves traveling at speeds different from light. Roughly 10 such theories were ruled out in a single observation. The measurement also tested whether gravity and light experience the same space-time. In some theories of quantum gravity, the effective speed of particles depends on their energy. Higher energy particles travel slightly faster or slower than lower energy ones, because the structure of space-time at the Planck scale affects different energy scales differently. For gravitational waves, which carry enormous collective energy, but with individual gravitons, each carrying extraordinarily small amounts, the 2017 observation constrained these speed-dependent effects in ways that loop quantum gravity models must accommodate. Beyond the physics, the observation established a new field, multi-messenger astronomy. For the first time, a single event was observed in both gravitational waves and light. Astronomers saw the neutron star merger unfold in real time across the entire electromagnetic spectrum, from radio waves to gamma rays, while simultaneously watching the gravitational wave signal evolve. The combination told physicists things about neutron star interiors, the origin of heavy elements, and the behavior of matter at nuclear densities that neither gravitational wave observation nor light observation could reveal alone. Each neutron star merger of this kind releases gravitons, enormous numbers of them, traveling together as a wave. Each graviton carries a tiny quantum of gravitational energy. By the time the wave reaches Earth after crossing 130 million light-years, the individual gravitons are spread across a wavefront miles wide and arrive scattered across a detection window of seconds. Isolating a single one is physically impossible with any instrument that could exist. But knowing they are there, knowing that gravity traveled at the speed of light from a cataclysm 130 million light-years away, is a form of indirect confirmation that is, in its own way, profound. The graviton has not been detected, but it left tracks. A detector large enough to catch a single graviton would need to be the size of a gas giant planet. But several groups of physicists have proposed a different strategy entirely. Look for quantum gravity without detecting a graviton at all. Look instead for the signature that quantum mechanics leaves on gravity, even at scales where individual gravitons cannot be resolved. The central idea comes from quantum information theory. If gravity is quantum mechanical, then gravity should be able to create quantum entanglement between masses, the strange correlation between particles, where measuring one instantly determines the state of the other, regardless of distance. Two masses, each in a quantum superposition of positions, placed close enough that they interact gravitationally, should become entangled with each other through their gravitational interaction. Entanglement between particles requires a quantum mediator. If gravity can create entanglement between two masses, the mediating field, the gravitational field, must be quantum. A classical, non-quantum gravitational field cannot generate entanglement, so measuring entanglement induced by gravity would prove that gravity is quantum mechanical without ever capturing an individual graviton. This experiment, proposed by physicists Sugato Bose, Vlatko Vedral, Chiara Marletto, and Marcus Aspelmeyer, among others, is called a quantum gravity entanglement experiment. In principle, it is straightforward. Take two small masses, put each one into a quantum superposition of two positions, allow them to interact gravitationally for a period of time, then measure whether they have become entangled. In practice, the challenges are enormous. The masses involved must be small enough to be placed in quantum superposition, a technically heroic task since quantum superposition is fragile and breaks down under any interaction with the environment. They must also be massive enough that their gravitational interaction is measurable. The overlap between these two requirements is a narrow window, currently at the edge of what experimental technology can reach. Masses of roughly a microgram, a millionth of a gram, appear to be in the feasible range, and experiments are underway in several countries. A positive result would be the most important discovery in physics, since the detection of gravitational waves. It would prove quantum gravity exists as a physical phenomenon. It would validate the graviton picture at some indirect level, and it would do so without building a Jupiter-sized detector. A negative result, masses that interact gravitationally without becoming entangled, would be deeply strange. It would suggest that gravity is somehow exempt from quantum mechanics, that there is a regime in which a classical force coexists with quantum matter, which would require completely new physics of a kind nobody currently has a framework for. Either outcome transforms our understanding. The experiment tests not just whether gravity has a quantum particle carrier, but whether gravity is quantum at all. The graviton question and the quantum gravity question are related but distinct, and right now, an answer to the second might arrive before we ever directly address the first. Somewhere between the engineering of quantum superposition for microgram masses and the theoretical prediction of the Planck scale, a thin thread of experimental possibility connects our ordinary laboratories to the deepest structure of reality. But even if those experiments confirm quantum gravity, the hardest question remains untouched. Why is the Planck scale, where quantum gravity fully reveals itself, so far beyond any energy we could ever reach? Every theory has a domain. Newtonian mechanics works beautifully for objects at everyday speeds and everyday sizes. General relativity takes over when masses are huge or speeds are close to the speed of light. Quantum mechanics governs the very small. Each theory has a boundary, beyond which something else is needed. The Planck scale is the boundary where quantum mechanics and gravity must both be taken seriously at the same time. The scale where neither theory can be ignored, and where both break down in their current form. The Planck length is roughly 10 to the power of negative 30 to 5 meters. Visualize a proton, already invisibly small. The Planck length is about 100 million billion times smaller than a proton. The Planck energy, the energy needed to probe structures at the Planck length, is roughly 10 to the power of 19 times the mass energy of a proton. That is the energy scale of the graviton's full quantum nature. The most powerful particle accelerator humans have ever built, the Large Hadron Collider in Switzerland, accelerates protons to energies about 10 million billion times smaller than the Planck energy. To build an accelerator that reaches the Planck scale using conventional technology would require a ring of superconducting magnets, larger than the Milky Way galaxy, powered by something far beyond any energy source we have ever conceived. The Planck scale is unreachable by direct experiment, permanently by any technology extrapolated from current physics. This creates a genuine philosophical problem for physics. The theory of quantum gravity, whatever it turns out to be, contains predictions about what happens at the Planck scale. If those predictions can never be tested, is quantum gravity science? Can a theory be considered scientific if its central predictions lie behind an experimentally impenetrable wall? Most physicists answer yes, with caveats. Quantum gravity theories often make predictions at accessible energy scales too. Corrections to gravitational wave propagation, subtle effects on black hole thermodynamics, modifications to cosmological perturbations from the early universe. These accessible predictions can, in principle, test aspects of quantum gravity indirectly, but the core physics of the Planck scale stays hidden. One indirect window does exist, and it is the most extraordinary laboratory in nature: black holes. Black holes concentrate mass into the smallest possible volumes. Near the singularity at a black hole's center, space-time curvature reaches values that approach Planck scale intensity. The physics at the heart of a black hole is Planck scale physics. We cannot visit a singularity, and we cannot retrieve information from inside a black hole's event horizon. But black holes affect the space around them, emit Hawking radiation, and leave observable signatures in the gravitational wave signals from their mergers. Hawking radiation, the slow evaporation of black holes through quantum effects, connects quantum mechanics and gravity in a way that no other known phenomenon does. Its spectrum carries, in principle, information about the quantum structure of space-time. Whether that information is readable from the outside is the subject of one of the most contested debates in theoretical physics today. The Planck scale is a wall, but walls have shadows, and those shadows fall where we can see them. The art of quantum gravity research is learning to read those shadows precisely enough to deduce what lives on the other side. The hierarchy problem, gravity's extreme weakness compared to every other force, has haunted physicists for decades. Proposed solutions come in many forms, and the most geometrically dramatic is this. Gravity is weak because it is sharing itself across dimensions of space that we cannot see. Our everyday experience is three-dimensional: left, right, forward, backward, up, down. Every measurement we have ever taken, every structure we have ever built, every physical theory we have ever tested operates within these three dimensions. We have no direct experience of any others. But mathematics allows more, and physics does not forbid it. Several well-developed theoretical frameworks predict that extra dimensions of space exist, compactified, curled up at scales too small to detect with any current instrument. In 1990, 9 physicists, Nima Arkani Hamed, Savas Dimopoulos, and Gia Diwali, proposed a model, now called the Large Extra Dimensions Model, that offered a new answer to the hierarchy problem. Suppose the three forces of the standard model, electromagnetism, the weak force, the strong force, are confined to our three-dimensional slice of a higher dimensional space, the way water waves are confined to the surface of an ocean, even though the ocean has depth. The particles of matter and the force carriers of the standard model live on a membrane, unable to leave it. Gravity, carried by the graviton, does not have to obey this confinement. The graviton, unlike the other carriers, is not a gauge boson of the standard model. It couples to energy everywhere, and everywhere includes the extra dimensions. So while electromagnetism and the strong and weak forces saturate our three dimensions with their full strength, gravity dilutes itself across all the dimensions. The fraction that remains in our three dimensions is tiny. We experience gravity as weak because we only see its three-dimensional shadow. The model made a specific and testable prediction. If large extra dimensions exist, gravity should behave normally at long distances, but deviate from the inverse square law at short ranges comparable to the size of the extra dimensions. At distances shorter than the extra dimension scale, gravity would become stronger faster than the inverse square law predicts. Experiments have tested gravity strength at distances as small as about 50 micrometers, using torsion pendulums, devices that measure tiny gravitational forces between small masses with extraordinary precision. So far, gravity follows the inverse square law down to those scales. This rules out extra dimensions larger than roughly 50 micrometers. A more mathematically structured version of the extra dimension idea, called the Randall-Sundrum model, proposed extra dimensions that are curved rather than flat, warped by the geometry of a higher dimensional space. In this framework, the Planck scale in the extra dimension is large, but the effective Planck scale felt in our three dimensions is exponentially suppressed by the curvature. The hierarchy between gravity and the other forces emerges from geometry, and the extra dimension could be of any size, possibly even infinite in extent, without conflicting with observations. In the Randall-Sundrum picture, the graviton has partner particles called Kaluza-Klein gravitons, versions of the graviton resonating in the extra dimension at higher masses. If the extra dimension exists, these particles would be produced at sufficiently high energies in a particle accelerator. The Large Hadron Collider searched for them and found nothing in the energy ranges it accessed. The search continues at higher energies as the accelerator's capabilities expand. If extra dimensions exist, the graviton we would detect in our three-dimensional world is only a piece of the full story. The true graviton propagates through all the dimensions simultaneously. What we call the graviton is its projection onto our slice of reality. And if our slice of reality is genuinely a projection, a shadow of a higher dimensional structure, then everything we have ever measured is an incomplete picture. The universe we call home may be the surface of something far larger, stranger, and richer than our three dimensions allow us to imagine. In 1993, physicist Gerard Hooft proposed something that sounded more like philosophy than physics. He suggested that everything happening inside a volume of space, every particle, every interaction, every quantum of information, could be completely described by a theory living on the surface surrounding that volume. No information inside the volume would be lost or missing from the surface description. The interior and the surface would be equivalent. A few years later, Leonard Susskind formalized this into what he called the holographic principle. The name comes from optical holograms, where a three-dimensional image is encoded on a two-dimensional film. The holographic principle says the universe might work the same way, three-dimensional physics encoded on a two-dimensional boundary. This sounds abstract. The graviton makes it concrete and urgent. In 1997, physicist Juan Maldacena published what became the most cited paper in the history of high-energy physics. He proposed a precise mathematical equivalence between two theories: a theory of quantum gravity, including strings in a five-dimensional curved spacetime, and a quantum field theory with no gravity at all, living on the four-dimensional boundary of that spacetime. The two theories, despite living in different numbers of dimensions, and one having gravity while the other does not, describe exactly the same physics. This equivalence is called the anti-de Sitter conformal field theory correspondence. What this means for the graviton is striking. On the gravity side of the correspondence, gravitons propagate through the five-dimensional bulk. On the boundary side, there are no gravitons, only strongly interacting quantum fields with no gravitational component whatsoever. Yet the two descriptions are mathematically identical. Every graviton state in the bulk has a precise counterpart in the boundary theory, expressible entirely in terms of non-gravitational quantum fields. Gravity in this picture is dual to something that contains no gravity. The graviton is real on one side of the correspondence and absent on the other, yet both sides describe the same reality. This duality has been extraordinarily productive Calculations that are impossibly hard on the gravity side become tractable on the boundary field theory side, and vice versa. Physicists have used it to calculate properties of quark-gluon plasma, model superconductors, and study information flow in strongly coupled systems. The correspondence works. It produces correct results. Its mathematical consistency has been verified in hundreds of different ways across dozens of subfields. But it raises a question with no comfortable answer. If gravity is dual to a non-gravitational theory, is gravity fundamental? Or is it emergent, a large-scale description that appears when you look at a non-gravitational quantum system from the outside? If gravity is emergent, then the graviton is emergent too. It is a collective excitation of underlying degrees of freedom that are not themselves gravitational. Like a sound wave in air, a photon that behaves like a particle and carries energy but is ultimately just coordinated motion of air molecules. The photon is real and useful. The individual air molecules are the true substrate. In this analogy, the graviton is the photon, and the boundary quantum field theory provides the molecules. A holographic principle does not prove this. The anti-de Sitter conformal field theory correspondence applies to a specific type of curved spacetime that may or may not describe our actual universe. Extending the correspondence to cosmological spacetimes resembling our own remains an open problem. But the existence of even one precise example where gravity is dual to a non-gravitational theory has permanently changed how physicists think about what gravity is. The graviton might be real, or it might be a description we use because it works, while the truly fundamental physics lives somewhere it casts no shadow. Stephen Hawking showed in 1974 that black holes are not entirely black. Quantum mechanics applied near the event horizon, the point of no return, surrounding a black hole, predicts that black holes slowly emit radiation, now called Hawking radiation, at a temperature that depends on their mass. The smaller the black hole, the hotter it is. As it radiates, it loses mass. As it loses mass, it gets hotter. The process accelerates until the black hole evaporates entirely. Hawking radiation is where quantum mechanics and gravity meet in the only natural laboratory we know of. Here is what happens at the event horizon in quantum mechanical terms. Empty space is never truly empty. Virtual particles constantly appear in pairs, one particle and one antiparticle, separated for an instant and then annihilating back into nothing. Near the event horizon of a black hole, something different can happen. If a pair appears with one particle just inside the horizon and one just outside, the inside particle falls toward the singularity, while the outside particle escapes. The black hole absorbs one particle and emits the other. The escaping particle is Hawking radiation. The energy carried away by that radiation comes from the black hole's own mass, through the equivalence of mass and energy. The black hole is slowly converting its mass into radiation. Every particle emitted carries away a small quantum of gravitational energy. In the language of the graviton, Hawking radiation includes gravitons. The black hole emits gravitational quanta along with photons and other particles. Black holes are the universe's only natural graviton factories operating at energies approaching the Planck scale. Around a Planck mass black hole, the smallest black hole consistent with quantum gravity, with a mass close to about 22 micrograms. The gravitational field at the horizon is so strong that the pair production rate of gravitons becomes comparable to the pair production rate of other particles. At this scale, gravity is as strong as the other forces, and the hierarchy problem disappears. Hawking's calculation used what physicists call the semi-classical approximation, quantum fields on a classical curved spacetime background. He treated the black hole's geometry with general relativity while treating the fields around it with quantum mechanics. The result is a prediction. Hawking radiation exists, but the calculation breaks down as the black hole shrinks toward the Planck scale. At that point, the quantum nature of the spacetime itself cannot be ignored, and a full theory of quantum gravity is required to describe what happens. The central unresolved question is what happens to the information that falls into a black hole. According to quantum mechanics, information is conserved, it can be scrambled and hidden, but never destroyed. According to Hawking's original calculation, The radiation coming out of a black hole is perfectly thermal. It carries no information about what fell in. A book and a brick falling into a black hole would produce identical radiation. If that is correct, quantum mechanics is violated. Information is genuinely destroyed. That contradiction, called the black hole information paradox, has driven theoretical physics for 50 years. Its resolution almost certainly requires a full theory of quantum gravity, a theory that tells us what the graviton is at the Planck scale and what happens to information at a singularity. Recent work, particularly the calculation of the page curve for evaporating black holes, suggests that information is preserved in Hawking radiation, that the radiation is subtly, non-thermally correlated in ways that encode everything that fell in. But the mechanism by which this happens, the precise gravitational physics near the singularity, remains unknown. The graviton is the key that unlocks these questions, and the answers, when they arrive, will rewrite our understanding of what information means in a universe governed by both quantum mechanics and gravity. Every particle in nature has an antiparticle, a partner with the same mass but opposite charge. The antiparticle of the electron is the positron. The antiparticle of the quark is the antiquark. When a particle meets its antiparticle, they annihilate, converting their combined mass into pure energy. Some particles are their own antiparticles. The photon is the clearest example. A photon carries no electric charge, no color charge, no weak isospin, none of the quantum numbers that distinguish a particle from its antiparticle. A photon and an antiphoton are identical. Physicists call such particles Majorana particles, after the Italian physicist Ettore Majorana, who analyzed this possibility. The graviton is expected, by nearly all theoretical frameworks, to be its own antiparticle. The reasoning follows directly from its properties. The graviton carries no charge. It is electrically neutral. It carries no color charge. It has no conserved quantum number that could distinguish it from an antigraviton. Its defining properties are its mass, which is 0, and its spin, which is 2. Both the graviton and a hypothetical antigraviton would have mass 0 and spin 2. They would be indistinguishable. This has a clean physical consequence. A graviton moving in one direction carries a spin of +2 along its direction of motion. In quantum mechanics, this is called helicity. The same particle moving in the opposite direction, or equivalently viewed from the time-reversed perspective, carries a helicity of -2. These two helicity states, +2 and -2, are the two polarization states of the graviton, and they belong to the same particle. No separate antigraviton is needed. Contrast this with the W bosons of the weak force. The W+ and W- are genuine antiparticles of each other. They carry opposite electric charges and are distinct particles. The photon and the Z boson are their own antiparticles. The graviton falls into the same self-conjugate category as the photon and Z boson. Why does this matter beyond particle taxonomy? The Majorana nature of the graviton connects to the symmetries of the theory and to the question of what quantum numbers gravity can violate or conserve. In some theories of quantum gravity, particularly those connected to supersymmetry, the graviton has a superpartner called the gravitino, a spin 3/2 particle that mediates gravity in the supersymmetric framework. The gravitino's Majorana or Dirac nature depends on how supersymmetry is broken, and that has observable consequences for cosmology. A Majorana gravitino decays differently from a Dirac one, leaving different signatures in the abundances of light elements produced in the first minutes after the universe's origin. Supersymmetry remains unconfirmed. The Large Hadron Collider has found no evidence for superpartner particles at the energy scales it has explored. But the gravitino, as the superpartner of the graviton, remains a live theoretical possibility, a second force carrier for gravity operating in a supersymmetric universe, connecting quantum gravity to cosmology in a way that produces testable predictions about the early universe. The self-conjugate nature of the graviton is one of its cleaner theoretical properties, one of the things we can say with reasonable confidence based on the structure of the theory, even without direct detection. It is a property predicted not by measurement, but by mathematics. And in the absence of experiments that can touch the graviton directly, mathematics is the only tool we have. In 2010, Physicist Eric Verlinde published a paper that unsettled a significant portion of the theoretical physics community. His proposal was direct. Gravity is a thermodynamic force. It is not a fundamental interaction at all. It arises from the statistical behavior of microscopic degrees of freedom, the same way pressure in a gas arises from the average collisions of countless molecules. If Verlinde is right, then searching for a graviton is like searching for a particle that carries the force of temperature. The question is malformed from the start. Verlinde's starting point was an observation made decades earlier by physicists Jacob Bekenstein and Stephen Hawking. The entropy of a black hole, the measure of its information content, is proportional to its surface area, not its volume. For any other object, entropy scales with volume. A box twice as large has roughly twice as many possible internal states. Black holes break this rule. Their entropy lives on the boundary. This is the root of the holographic principle, and it suggests that the fundamental degrees of freedom of gravity are two-dimensional, surface-like quantities rather than three-dimensional volumetric ones. Verlinde took this seriously and derived Newton's law of gravitation from pure thermodynamic reasoning applied to an entropic force on a holographic surface. An entropic force is a force that arises because a system tends toward higher entropy, toward the state with the most possible configurations. Entropy wants to grow, and its growth, in Verlinde's framework, manifests as what we call gravitational attraction. The result is striking. From thermodynamics alone, assuming only that entropy is proportional to area and temperature to surface gravity, you recover Newton's law of gravity. The gravitational constant emerges from statistical mechanics. No graviton is needed. No quantum of the gravitational field appears. Gravity is the macroscopic average of a microscopic average of microscopic molecular motion. Verlinde extended this to general relativity and, more controversially, proposed that dark matter, the invisible mass inferred from galaxy rotation curves and other observations, does not exist as a particle. Instead, he argued that the behavior attributed to dark matter is a correction to gravity arising from the emergent nature of the force itself. In his framework, the entropy associated with ordinary matter interacts with the entropy of the underlying microscopic degrees of freedom. He calls them dark energy degrees of freedom. And the resulting modification to gravity mimics the presence of extra mass. This prediction is testable. Verlinde's theory makes specific predictions about the relationship between the distribution of ordinary matter in galaxies and the apparent dark matter distribution inferred from rotation curves. Some observational analyses have found agreement with his predictions at a level that cannot be dismissed. Others find significant tensions. The mainstream of the theoretical physics community remains skeptical. Verlinde's framework lacks a microscopic theory. He cannot identify what the underlying degrees of freedom actually are. The derivations, while suggestive, have not been cast in a form that allows precision predictions comparable to general relativity. And the approach does not yet account for all cosmological observations in a consistent way. But the idea that gravity is emergent, and the graviton therefore an effective rather than fundamental description, has taken permanent root in serious theoretical physics. Whether or not Verlinde's specific proposal is correct, the question it raises is genuine. Is the graviton a fundamental particle, or a collective excitation of something deeper? That question has no agreed answer, and chasing it takes us somewhere even stranger. In 1967, physicists Bryce DeWitt and John Wheeler wrote down an equation that was supposed to be the quantum mechanical equation of the entire universe. They applied the standard quantization procedure to general relativity, treating the geometry of all of space as the quantum variable, and arrived at a single equation governing the wave function of the universe itself. The equation works, it is mathematically consistent, and it contains no time variable, none, absent. The equation describes a universe frozen in an eternal quantum superposition of all possible geometries, with no reference to when anything happens, no evolution, no flow of time. The wave function of the universe satisfies an equation that treats all moments as simultaneous, or rather, as having no temporal order at all. This is called the problem of time in quantum gravity, and it is one of the deepest conceptual puzzles in all of physics. In ordinary quantum mechanics, time is a background parameter. The wave function of a particle evolves according to the Schrödinger equation, and time appears explicitly as the variable along which the evolution happens. Time is fixed, external, and not subject to quantum fluctuations. It is the stage on which quantum mechanics plays out. In general relativity, time is flexible. It stretches and compresses depending on how fast you move and how strong gravity is. Two observers moving differently through spacetime measured different durations between the same two events. Time is not a fixed background. It is part of the dynamical fabric of spacetime itself. When you try to combine these two frameworks into a single quantum theory of gravity, time cannot be both things simultaneously. It cannot be the fixed parameter along which quantum evolution happens and the flexible dynamical quantity that general relativity requires. Something must give. What gives in the Wheeler-DeWitt equation is time's role as an evolution parameter. The equation treats the universe as a static object, a single unchanging quantum state, rather than something that evolves. Where does time come from then? How do we experience a clear sense of past, present, and future if the fundamental equation of the universe has no time in it? The leading answer is that time is emergent. In a sufficiently complex quantum system, a universe containing vast numbers of interacting degrees of freedom, certain subsystems can use each other as clocks. One part of the universe measures change in another part. The correlation between these subsystems, when coarse-grained and averaged over the quantum fluctuations of geometry, produces the smooth flow of time that we experience. Time is not a fundamental feature of reality. It is what happens when quantum systems with many degrees of freedom observe each other. This connects back to the graviton in a subtle way. If time is emergent, and gravity is the force that governs the dynamics of space-time, then the graviton, the quantum of the gravitational field, exists in a framework where time itself is derived from something more fundamental. A graviton, in this picture, is not a particle propagating through time. It is a fluctuation in a timeless quantum geometry, and time emerges from the collective behavior of many such fluctuations, averaged together. The implications reach further than physics. If time emerges from quantum gravity, then our intuition about cause and effect, before and after, is a large-scale approximation. At the Planck scale, the concepts of earlier and later may have no meaning. Events do not happen in sequence, they simply correlate. And if that is true, then the universe at its deepest level is not a story that unfolds. It is a pattern that simply is. The graviton connects to what is arguably the single greatest numerical failure in the history of science. In 1998, two independent teams of astronomers measuring distant supernovae discovered that the expansion of the universe is accelerating. Distant galaxies are flying away from us faster now than they were billions of years ago. Something is pushing space apart. Physicists call this something the cosmological constant, an energy density intrinsic to empty space, present even when all matter and radiation have been removed. The measured value of the cosmological constant is extraordinarily small. In natural units of quantum gravity, the Planck units, it is a number with a decimal point, followed by 122 zeros, before the first significant digit. A 1 followed by 122 zeros, smaller than what theory predicts. Here is where the graviton becomes central. In quantum field theory, empty space is not truly empty. Virtual particles constantly fluctuate in and out of existence. Each of these fluctuations carries energy, the energy of the vacuum. The zero-point energy of all quantum fields, added together, should contribute to the cosmological constant. When physicists calculate the expected contribution of all known quantum fields, including the gravitational field and its gravitons, the answer is approximately 1 in Planck units. The observed value is 10 to the power of negative 122 in Planck units. The discrepancy between the prediction and the observation is a factor of 10 to the power of 122, the largest numerical discrepancy between theory and experiment in the history of science, by an enormous margin. The graviton matters here because quantum gravity fluctuations contribute to vacuum energy. Gravitons themselves, as quanta of the gravitational field, carry energy that fluctuates at every scale, up to the Planck energy. When you sum those contributions, the result dwarfs the observed value of the cosmological constant by the same catastrophic factor. Some cancellation mechanism must be at work. Either the contributions from different quantum fields cancel each other almost perfectly, requiring a fine-tuning of 1 part in 10 to the power of 122, which is so precise it strains any notion of naturalness, or our understanding of how quantum fields contribute to vacuum energy is fundamentally wrong. Supersymmetry offers a partial solution. In a perfectly supersymmetric universe, the vacuum energy contributions of bosons, force-carrying particles, and fermions, matter particles, cancel exactly because they contribute with opposite signs. The cosmological constant would be precisely zero, but supersymmetry is broken in our universe. Particles and their superpartners have different masses, which is why we have not detected superpartners yet. The breaking of supersymmetry reintroduces a vacuum energy contribution, though smaller than without supersymmetry. The result is still orders of magnitude too large. The anthropic argument, associated with the string theory landscape, suggests that the cosmological constant has the value it has because only universes with small cosmological constants can form galaxies, stars, and observers. In the vast multiverse of possible string theory vacua, most universes have a cosmological constant so large that space expands too fast for structure to form. We find ourselves in a rare, fine-tuned vacuum because only such vacua permit our existence. This argument is controversial. Some physicists find it compelling. Others find it a capitulation that abandons the project of explanation. The cosmological constant problem is where the graviton story intersects with the largest structures in the universe. The force that shapes galaxies and drives the universe's expansion connects, through its quantum particle, to a numerical mystery that our best theories cannot resolve. Quantum mechanics has an unresolved problem at its core that most introductory courses gloss over. It is called the measurement problem, and it gets dramatically worse when gravity enters the picture. In ordinary quantum mechanics, a particle does not have a definite position, momentum, or energy until it is measured. Before measurement, the particle exists in a superposition, a combination of multiple possible states simultaneously. When a measurement happens, the wave function collapses to one definite outcome. But the theory does not explain why or how the collapse happens. The mathematics of quantum mechanics describes the evolution of superpositions perfectly well, but it says nothing about why measurement produces a single definite result. This is the measurement problem. Various interpretations of quantum mechanics, the Copenhagen interpretation, many worlds, ohmium mechanics, objective collapse theories, handle it differently. None is universally accepted. The problem has been with the theory since its birth. Now add gravity. A mass in a quantum superposition of two positions has a quantum superposition of two gravitational fields. Space-time is curved differently depending on where the mass is. In a superposition of positions, space-time is in a superposition of geometries. The gravitational field, and therefore the graviton field, is in a superposition of configurations. Roger Penrose proposed in the 1990s that this superposition of space-time geometries is unstable. Gravity, he argued, does not permit indefinite superpositions of macroscopically different geometries. The uncertainty in space-time geometry associated with a quantum superposition of mass positions creates an instability that causes spontaneous collapse after a time that depends on the mass involved. Larger masses collapse faster. The gravitational influence of the superposed mass on itself, mediated by gravitons, triggers a self-measurement that resolves the superposition into one outcome. Penrose's proposal is called objective reduction, or OR, when extended to biological systems. In its basic physical form, it predicts that superpositions of large enough masses collapse spontaneously after predictable timescales without any external measurement. This is a testable prediction. Current experiments pushing quantum superposition to microgram masses are approaching the regime where Penrose's predicted collapse times become relevant. If superpositions of microgram masses collapse faster than any known environmental decoherence can explain, Penrose's gravitational collapse mechanism gains credibility. The measurement problem in quantum gravity goes deeper still. In ordinary quantum mechanics, the observer is external to the system. A measuring device outside the quantum system collapses its wave function. In quantum cosmology, the system is the entire universe. There is no external observer. The Wheeler-DeWitt equation describes a universe with no external perspective, no outside measuring device, and no mechanism for the wave function of the universe to collapse. In this context, the graviton is not just a particle, it is a feature of a quantum state that the universe itself is in. Every observation any of us has ever made has happened inside the wave function of the universe, inside the quantum gravitational state described by the Wheeler-DeWitt equation. What collapse means in that context, and whether it means anything at all, is completely open. Quantum gravity does not just challenge our understanding of space and time. It challenges our understanding of what it means to know something, to measure something, to observe reality. The graviton sits at the center of that challenge as the quantum of the field that, if quantized, makes the stage itself a quantum system. One of the most elegant experimental strategies for probing quantum gravity requires no particle accelerator, no Jupiter-sized detector, and no laboratory at all. It requires only a telescope and an extraordinarily distant catastrophic event. The idea is this: if spacetime has a quantum structure at the Planck scale, if it is discrete, foamy, or otherwise granular at the smallest distances, then particles traveling through it at very high energies might interact with that structure in a way that depends on their energy. Higher energy photons, or gravitons, might travel very slightly faster or slower than lower energy ones. Over cosmological distances, even a tiny energy-dependent speed difference would accumulate into a measurable time delay between photons of different energies arriving from the same distant event. This effect is called Planck scale dispersion. It appears in some models of loop quantum gravity and other discrete space-time approaches. In string theory, the predictions depend on specifics of the compactification, how the extra dimensions are structured. In some string models, there is no dispersion. In others, there is. Gamma-ray bursts are the ideal source for testing this. They are the most energetic explosions in the universe, releasing more energy in a few seconds than the star that produced them released over its entire life. They occur at cosmological distances, billions of light years away, and they emit photons across a huge range of energies simultaneously. If Planck scale dispersion exists, the highest energy photons should arrive systematically earlier or later than the lowest energy ones, with the time difference scaling with the distance to the source. The Fermi Gamma-ray Space Telescope, launched in 2008, was specifically designed to be sensitive to this effect. After analyzing gamma-ray bursts at distances of billions of light years, the results are clear. No energy-dependent time delay has been detected. The most energetic photons arrive at the same time as lower energy ones, to a precision that constrains any Planck scale dispersion to be smaller than the Planck length divided by the photon's energy, times the speed of light. That constraint is extremely tight. It rules out a wide range of models that predicted detectable dispersion at the Planck scale, particularly the simplest linear dispersion models. Some more complex models with quadratic or higher-order dispersion remain consistent with the data. For gravitons specifically, the 2017 neutron star merger set independent constraints. Gravitational waves and gamma rays from the same event arrived within seconds of each other after traveling 130 million light-years. Any energy-dependent dispersion in the graviton's speed must be even smaller than the constraints from photons, given the long distance and simultaneous detection. These measurements narrow the space of viable quantum gravity theories. They cannot directly detect a graviton, but they constrain the medium through which gravitons travel, the fabric of space-time, and rule out models of that fabric that predict observable Planck-scale deviations from classical geometry. The absence of dispersion is, in its own way, a profound result. It tells us that space-time, whatever its quantum nature at the Planck scale, appears smooth and continuous at every scale we have been able to probe so far. The quantum structure, if it exists, is subtler than the most straightforward predictions of discrete space-time models. The universe is giving us answers. They are just answers to questions we did not quite ask, from events we did not plan, at distances that dwarf anything human hands have built. Every particle that falls into a black hole carries information. The particular arrangement of its quantum state, its spin, its momentum, its entanglement with other particles, is a specific, irreplaceable record of its history. Quantum mechanics guarantees that this information cannot be destroyed. It can be scrambled beyond any practical recovery, but the physics of quantum mechanics requires it to persist somewhere, encoded in the state of the universe. A black hole is the most extreme scrambler in nature. Everything that crosses the event horizon is hidden from the outside universe by gravity, so strong that even light cannot escape. The information about what fell in appears, from the outside, to be completely lost. Hawking's calculation in 1974 made this worse. The radiation a black hole emits as it evaporates is thermal. It has the character of random heat radiation, carrying no information about what fell in. If a black hole forms from a collapsing star, swallows a library's worth of books, and then completely evaporates into thermal radiation, where did the information in those books go? If it is truly gone, quantum mechanics is violated. Information is destroyed. That is called the information paradox. For gravitons, the paradox has a specific form. Gravitons that fall into a black hole carry information about the gravitational state of whatever produced them. Gravitons emitted as Hawking radiation carry the thermal spectrum Hawking predicted. If the outgoing gravitons carry no information about the infalling gravitons, gravitational information is lost. The resolution proposed by most theorists today is that information is preserved in Hawking radiation, but the mechanism is subtle, non-local, and deeply connected to quantum gravity. The leading modern approach uses the holographic principle. The black hole, viewed from the outside, is described by a quantum theory on its event horizon. This boundary theory is unitary. It conserves information by the rules of quantum mechanics. From the boundary perspective, infalling matter does not disappear into a singularity. It is scrambled across the horizon degrees of freedom and re-emitted as radiation that is thermally random-looking, but secretly delicately correlated. The Page curve describes how information leaks out during black hole evaporation. The entanglement entropy of the Hawking radiation first grows, as expected for thermal radiation, then turns around and decreases as the black hole shrinks, an effect that would only happen if the radiation carries information. Recent calculations using a technique called the replica trick and the concept of islands in the space-time geometry confirm that the Page curve is recovered when quantum gravity effects near the singularity are properly accounted for. The concept of islands is particularly striking. The calculation shows that regions inside the black hole, inside the event horizon, contribute to the quantum state of the radiation outside. Information is not purely local. The interior and the exterior are quantum mechanically correlated in ways that violate the intuition that what is inside a black hole stays inside. Gravitons participate in this process as carriers of gravitational information. The quantum gravitational field at the horizon is where the scrambling happens, where ingoing quantum states are mixed and re-emitted. The graviton in this picture is both the agent of the black hole's gravitational grip and a participant in the slow, subtle leak of information that saves quantum mechanics from the paradox. A complete solution to the information paradox requires a complete theory of quantum gravity. Every step toward that solution teaches us something about what the graviton fundamentally is and how gravity operates at the boundary between quantum mechanics and the geometry of space-time. The Laser Interferometer Gravitational Wave Observatory changed astrophysics forever. Its successors may change physics at a deeper level still, not by detecting a graviton, but by probing the quantum nature of gravity through the most sensitive measurements of gravitational waves ever made. The Einstein telescope, planned for construction in Europe, will be a triangular underground detector with arms 10 kilometers long, more than twice the length of current detectors. Operating at temperatures close to absolute zero, shielded from seismic noise by its underground location, and using quantum squeezing of light to push below the standard quantum limit of measurement, it will detect gravitational waves from events billions of light years away, with a sensitivity that current instruments cannot approach. The Laser Interferometer Space Antenna, scheduled for launch in the early 2030s, will operate in space with arm lengths of 2.5 million kilometers. At that scale, it becomes sensitive to gravitational waves at frequencies far lower than any ground-based detector can reach. Frequencies produced by the merger of supermassive black holes, by dense stars spiraling into galactic center black holes, and by a stochastic background of gravitational waves produced in the earliest moments of the universe. That primordial gravitational wave background is the most direct observational window onto quantum gravity in the early universe. In the fraction of a second after the universe's origin, quantum fluctuations in the gravitational field, quantum fluctuations in graviton modes, were stretched by the rapid expansion called inflation to cosmological scales. Those stretched fluctuations became the gravitational wave background that persists today. Detecting this background would give physicists a direct snapshot of the gravitational quantum field at the earliest accessible moment in cosmic history. Inflation predicts a specific amplitude and spectral tilt for the primordial gravitational wave background. Different models of quantum gravity predict subtle modifications to these features. A detection by a space-based gravitational wave observatory, combined with precision measurements of the cosmic microwave background, could distinguish between inflationary models that differ in their quantum gravitational predictions. Beyond these planned instruments, proposals exist for gravitational wave detectors using atom interferometry, using the quantum mechanical wave properties of atoms rather than laser light to measure spacetime strain. Atom interferometers in space could in principle reach sensitivities at which the quantum nature of the gravitational field begins to leave detectable traces in the noise properties of the measurement itself. None of these instruments will detect a single graviton. The arguments showing that individual graviton detection is impossible remain valid, but they will measure the collective behavior of graviton fields at sensitivities that begin to distinguish classical gravitational wave backgrounds from their quantum counterparts. The difference between a classical gravitational wave and a stream of gravitons shows up in the statistical correlations between measurements at different times and locations. Quantum fields produce correlations that classical fields cannot replicate. The next decade of gravitational wave astronomy is the closest humanity will come to experimental quantum gravity. Every detection, every constraint on the gravitational wave background, every measurement of a merger's waveform carries encoded information about the quantum field responsible for gravity. The graviton hides in every signal. We just need instruments subtle enough to read the handwriting it leaves behind. Science advances through confirmation and through falsification. A theory that cannot be tested in principle occupies an uncomfortable position. It may be correct, but it cannot be scientific in the classical sense. The graviton sits in exactly that position. Its direct detection appears physically impossible. So what does the absence of direct detection mean for physics? One answer is, nothing yet. The graviton's existence is not falsified by our inability to detect it individually. The impossibility argument tells us that no instrument we could build would catch a single graviton. It does not tell us the graviton does not exist. Gravitational waves are detected every time a binary black hole or neutron star merger is observed. Those waves are, by every theoretical expectation, composed of gravitons. The wave is detected even if the individual particle is not. Inability to isolate a single graviton no more disproves its existence than inability to isolate a single photon in a distant earthquake disproves that sound waves are quantum mechanical. A second answer involves what happens if quantum gravity experiments, the entanglement experiments, the primordial gravitational wave background measurements, the precision tests, all return results consistent with classical gravity. If every experiment sensitive to the quantum nature of the gravitational field finds no quantum signature, at some point the accumulation of null results becomes informative. It would not prove the graviton does not exist, but it would push physicists toward questioning whether quantum gravity is necessary in the first place. A third, more radical possibility is that the graviton framework is correct at some energy scale, but below a certain threshold, perhaps the Planck scale, perhaps lower. Quantum effects of gravity are so suppressed that the universe behaves, at all accessible scales, exactly as if gravity were classical. In this scenario, the graviton exists in principle, but plays no measurable role in any observation we could ever make. The theory is true and permanently untestable. Physicists have a term for a theory that is consistent with all observations and makes no new testable predictions, empirically equivalent to classical gravity at our energy scales. Such a theory is a valid description. It may even be the correct description, but it contributes nothing to scientific knowledge that classical general relativity does not already provide. The scenario that would truly shake physics is one where quantum gravity entanglement experiments return a null result at scales where quantum effects should be visible. If microgram masses interact gravitationally, without becoming entangled, and all other quantum effects are correctly accounted for, then gravity would be behaving classically in a context where the other forces are demonstrably quantum mechanical. That asymmetry has no explanation within any current theoretical framework. It would require a fundamentally new principle, something that singles out gravity as exempt from quantum mechanics in a way that no existing theory predicts. The absence of a detected graviton is currently a silence, not a statement. Every experiment constrains the space of viable theories without ruling out the graviton's existence. But the silence accumulates. Each null result narrows the possibilities. At some point, decades from now, perhaps, the accumulated constraints may tell us whether the graviton is an accurate description of a real quantum particle or the most sophisticated approximation in the history of science. Either outcome is, in its own way, a discovery. Supersymmetry is the theoretical proposal that every particle in nature has a partner particle with the same mass, but a different spin, specifically a spin that differs by 1/2. Bosons, which have integer spin, each have a fermionic superpartner with half-integer spin. Fermions, which have half-integer spin, each have a bosonic superpartner. If supersymmetry is correct, the graviton has a superpartner. It is called the gravitino. The gravitino has spin 2. The gravitino has spin 3/2, one of the highest spins possible for a fundamental particle. Like the gravitino couples to all forms of energy and momentum. Like the graviton, it is extremely weakly interacting. Unlike the gravitino has a mass when supersymmetry is broken, and the way that mass arises carries enormous consequences for cosmology. The gravitino mass depends on how supersymmetry breaks down, how the perfect symmetry between bosons and fermions gets disrupted in our universe. Different breaking mechanisms produce different gravitino masses, ranging from a few electron volts to masses trillions of times greater than the proton. This range matters because the gravitino's mass determines how it behaves in the early universe, what it decays into, and whether it causes problems for the standard picture of cosmic evolution. A gravitino that is too light is stable and contributes to the total energy density of the universe. If it is produced in too large a quantity in the hot early universe, it overproduces the total matter density, a problem called the gravitino overproduction problem. Cosmological constraints on the gravitino's mass and abundance place limits on the temperature the universe could reach after inflation, which in turn constrains how inflation ended and how matter was created. A gravitino heavier than roughly 100 billion electron volts decays before the formation of light elements in the first few minutes after the universe's origin. Its decay products can disrupt the production of helium and deuterium, whose observed abundances are one of the precision tests of early universe physics. Getting the right abundances sets limits on the gravitino's properties. In supergravity, the local version of supersymmetry, which includes gravity, the gravitino is the gauge field of local supersymmetry transformations, analogous to the way the photon is the gauge field of local electromagnetic transformations. The gravitino becomes massive by absorbing a Goldstone fermion, the partner of the field whose condensation breaks supersymmetry. This is the gravitational analog of the Higgs mechanism. Supersymmetry has not been confirmed. The Large Hadron Collider has searched extensively for superpartner particles and found none. Each round of exclusion pushes the predicted superpartner masses higher, which requires more fine-tuning in the theory and reduces its appeal as a natural solution to the hierarchy problem. Many physicists now consider simple supersymmetry unlikely to appear at accessible energies. But supersymmetry could still be correct at higher energy scales, and the gravitino could exist even if no other superpartners are light enough to produce in current accelerators. If supersymmetry is correct, the graviton has company. It is part of a super multiplet, a matched pair, the spin 2 graviton and the spin 3/2 gravitino, together forming the gravitational sector of a supersymmetric universe. And the gravitino, through its cosmological behavior, leaves traces in the earliest accessible moments of cosmic history. The gravitine, in a supersymmetric universe, is not alone. It has a partner, and that partner may be easier to find. The graviton, as we understand it, is the quantum carrier of the gravitational force, the particle that plays the same role for gravity that the photon plays for electromagnetism. Its existence follows from applying the framework of quantum field theory to the gravitational field. That framework has been spectacularly successful for every other force. But what if the graviton is not the final word? What if a deeper theory absorbs gravity into something more fundamental, making the graviton a derived concept rather than a basic ingredient? In the history of physics, this kind of absorption has happened before. Before Maxwell unified electricity and magnetism, the electric force and the magnetic force seemed like separate phenomena with separate carriers. Maxwell showed they were two aspects of a single electromagnetic field. The unification did not eliminate the photon. The photon became the carrier of the unified force, but the number of independent forces decreased by one. The electroweak unification in the 1960s went further. The electromagnetic force and the weak nuclear force were unified into a single electroweak force by Sheldon Glashow, Abdus Salam, and Steven Weinberg. At low energies, symmetry breaking makes them look different. At high energies, above the mass of the W and Z bosons, they merge into a single interaction. The photon, the W bosons, and the Z boson are all carriers of the unified electroweak force. Grand unified theories attempt to merge the electroweak force with the strong nuclear force at even higher energies, around a scale 10 trillion times higher than the energies produced by current accelerators. In these theories, all three non-gravitational forces are aspects of a single force at high energies. Adding gravity to a unified framework is the step no theory has successfully completed. String theory comes closest. It naturally incorporates gravity, and all forces in string theory arise from the vibrations of strings, suggesting a single underlying object. In the best developed string theories, the distinction between gravitons and other gauge bosons dissolves at the string scale. All of them are vibration modes of the same fundamental string. The graviton is unified with all other force carriers into a single framework, even if it remains distinct in terms of its properties at low energies. In loop quantum gravity, the situation is different. Gravity is quantized, but the other forces are not part of the framework. Unification in loop quantum gravity requires incorporating the standard model degrees of freedom into the spin network structure, a project underway but incomplete. The most radical proposals suggest that gravity is not an independent force at all, that it is a consequence of quantum information structure, entropy gradients, or geometric identities that emerge from more basic principles. In these approaches, asking what the graviton's fundamental nature is may be the wrong question, because the graviton might be a high-level description of something with no particle-like nature at its base, a complete theory of everything. If it exists, and if we find it, will answer whether the graviton is fundamental. It may reveal that the graviton is one face of a single unified object. It may reveal that gravity is emergent from non-gravitational physics. It may reveal that our current picture is an approximation so good it mimics the truth at every scale we can reach, while the actual truth operates in a framework we have not yet conceived. What that framework looks like, we genuinely do not know. And that is the deepest, most honest thing physics can currently say about the graviton. The universe began in a state of extraordinary density and temperature. In the first fraction of a second, it underwent a period of exponential expansion called inflation, a doubling and redoubling of its size, so rapid that a region smaller than a proton grew to the size of a grapefruit in less time than any clock could measure. Inflation solved several puzzles about the large-scale structure of the cosmos: why the universe looks the same in all directions, why it is geometrically flat, why it has no magnetic monopoles despite theories predicting them. During inflation, quantum fluctuations in every field were stretched to cosmic scales. The quantum fluctuations in the density of matter became the seeds of galaxies, the slight overdensities that eventually collapsed under gravity to form the large-scale structure of the universe we observe today. These density fluctuations have been measured with extraordinary precision in the cosmic microwave background, the afterglow of the early universe, and they match the predictions of inflationary models with remarkable accuracy. The quantum fluctuations in the gravitational field, the graviton field, were stretched in the same way. Those fluctuations became gravitational waves, a background of gravitational waves produced during inflation, called the primordial gravitational wave background, should pervade the universe today, carrying imprints of the quantum gravitational physics active during the first moments of cosmic time. These primordial gravitational waves, if detectable, would be the oldest signal in the universe. They were produced before the cosmic microwave background, before atoms formed, before nuclei formed, before any structure in the universe existed at all. They carry the direct imprint of quantum gravity during inflation. The amplitude of the primordial gravitational wave background is characterized by a quantity called the tensor to scalar ratio, the ratio of gravitational wave fluctuations to density fluctuations. Different inflationary models predict different values of this ratio. Measuring it would discriminate between models and reveal the energy scale at which inflation occurred. If the energy scale of inflation is close to the grand unified theory scale, the tensor to scalar ratio is large enough that next-generation experiments could detect it. Experiments searching for the signal look for a specific pattern in the polarization of the cosmic microwave background, called B-mode polarization. Density fluctuations produce only one type of polarization pattern. Gravitational waves produce an additional pattern that density fluctuations cannot generate. Detecting that extra polarization pattern in the microwave background would be a direct detection of the primordial gravitational wave background, a detection of the collective effect of the primordial graviton field. Current experiments, including the BICEP and Keck array telescopes operating near the South Pole, have set upper limits on the tensor to scalar ratio that rule out the simplest inflationary models. Future experiments from space, including the LIGHT satellite for the study of B-mode polarization and inflation, aim to push the sensitivity by another order of magnitude, potentially reaching the level predicted by the most motivated inflationary models. Detecting primordial gravitational waves would be the closest humanity has ever come to touching the quantum gravitational field directly. Every photon of B-mode polarization in the cosmic microwave background carries, encoded in its pattern, the memory of graviton quantum fluctuations that occurred before anything else in the observable universe existed. The graviton may never be caught individually, but it left its fingerprint at the beginning of time, and we are building instruments sensitive enough to read it. Everything in this story has built toward a possibility so fundamental that it reframes every question we have asked. What if space-time is not a basic ingredient of reality? What if space-time, distance, and geometry are collective properties that emerge from something more fundamental, something that has no spatial or temporal structure of its own? And if that is true, what does it mean for the graviton, which is defined as the quantum of the space-time metric? The evidence for this possibility has been accumulating from several directions simultaneously. The holographic principle says all the information in a volume of space is encoded on its boundary. This suggests that the three-dimensional geometry of the volume is not fundamental. It is a derived description of what happens on a two-dimensional surface. Gravity in 3 dimensions is dual to a non-gravitational theory in 2 dimensions. The three-dimensional geometry is the emergent structure. The two-dimensional theory is the more fundamental one. The Wheeler-DeWitt equation says time does not appear in the fundamental equation governing the universe. Time emerges from the correlations between subsystems. Space-time has no fundamental status in quantum cosmology. It appears as an approximate macroscopic structure when the quantum state of the universe is described from within. Quantum error correction, a concept from quantum computing, has emerged as a surprising tool for understanding how space-time geometry might be encoded in a boundary theory. Physicists Ahmed Almhiri, Shi Dong, and Daniel Harlow showed that the holographic correspondence has the mathematical structure of a quantum error-correcting code. The bulk spacetime is encoded in the boundary theory in a way that is redundant. Any local region of the bulk is reconstructible from multiple non-overlapping regions of the boundary. Spacetime geometry is, in this picture, a redundant encoding of quantum information. Mark van Ramsdonk extended this further. He showed that in the holographic correspondence, the entanglement between different regions of the boundary theory is directly connected to the connectedness of the bulk spacetime. If you mathematically cut the entanglement between 2 boundary regions, the corresponding bulk spacetime regions disconnect. They become causally separated. Entanglement weaves spacetime together. Remove the quantum correlations and spacetime tears apart. If spacetime is woven from entanglement, then the graviton, the quantum of the spacetime metric, is a quantum of the entanglement structure. A graviton is not a particle that exists in space-time and mediates gravity. It is a fluctuation in the entanglement pattern that constitutes space-time. Space-time and gravity are the same thing described at different levels of resolution, and both emerge from the quantum information structure of a more fundamental theory that has no geometry of its own. This picture is not yet a complete theory. The holographic correspondence applies to specific spacetimes that do not exactly match our universe. The connection between quantum error correction and the graviton dynamics of realistic cosmologies remains a research frontier. The precise microscopic degrees of freedom from which spacetime emerges have not been identified. But the direction is unmistakable. Every major advance in theoretical physics over the past 30 years has pushed in the same direction. Spacetime is not fundamental. Geometry is derived. The graviton is a description of an emergent phenomenon, not a fundamental particle in the way that the electron or the photon might be fundamental. If this is correct, then asking what the graviton really is has led us all the way down to the foundation of reality, and what we find at the bottom is not particles, not fields, not space-time, but quantum information, entanglement, correlation, the irreducible fact that parts of the universe are connected by shared quantum states, and that the geometry of space is what those connections look like from the inside. We started with a simple question: what is the graviton, and why have we never found one? The first part of the answer is clean. The graviton is the theoretical quantum carrier of the gravitational force, a massless particle with spin 2 that mediates gravity the way the photon mediates electromagnetism. Its properties follow from the mathematics of general relativity applied to quantum field theory. Its spin 2 nature is fixed by the geometry of gravity. Its masslessness is required by the infinite range of the gravitational force. Every calculation that attempts to treat gravity as a quantum field produces the graviton as an output. The second part of the answer is more honest and more interesting. We have never found one, because finding one appears to be physically impossible within any conceivable technology. A graviton detector, sufficient to catch a single quantum of the gravitational field, would need to be the size of a gas giant planet. The gravitational force is so weak that the quantum it carries leaves an imprint too faint for any instrument smaller than an astronomical object to register. But the deeper answer to both questions is that they may be asking about the wrong level of description. The graviton is the right description of gravity at low energies, at the energies accessible to any experiment, any observatory, any instrument we could build on Earth or launch into space. At those energies, treating gravity as a quantum field with a particle carrier is self-consistent, predictive, and correct. General relativity emerges from the classical limit of graviton exchange. Gravitational waves are coherent states of gravitons. The bending of light, the precession of orbits, the dynamics of black holes, all of these are reproduced by the graviton picture at the level of precision our best measurements reach. At high energies, at the Planck scale, at the temperatures that existed in the first instance of the universe, the graviton description breaks down. The theory becomes non-renormalizable. Probabilities exceed 1. The mathematics signals its own incompleteness. Something else takes over, and we do not yet know what that something is. String theory offers one answer. The graviton is a vibrational mode of a fundamental string, and at high energies the string nature reveals itself, resolving the infinities and providing a finite theory of quantum gravity. Loop quantum gravity offers another. The graviton is a long wavelength ripple in a discrete network of quantized spacetime, and at high energies, the network's granular structure becomes relevant. Emergent gravity offers a third. The graviton is a collective excitation of underlying degrees of freedom that are not themselves gravitational, and at high energies, those underlying degrees of freedom, whatever they are, take over. Each answer implies a different universe. Each implies a different nature. For space and time, a different story about what the cosmos is made of at its most fundamental level, and each remains to date unconfirmed by direct experiment. What we know for certain is this: the graviton is demanded by the logic of physics. The consistency of a quantum universe requires a quantum gravitational field, and a quantum gravitational field has quanta. Those quanta are gravitons. The force they carry shapes every structure in the cosmos, from the paths of particles to the geometry of the universe itself. And the particle carrying that force has never been directly observed by any instrument in human history. That absence is not a failure. It is an invitation. Every null result in graviton detection, every constraint from gravitational wave observatories, every precision test of gravity at small scales and cosmological scales narrows the space of what the graviton can be and how the universe can work. The search is already teaching us. The answers accumulating around the edges of the question are already changing how physicists think about space, time, information, and the nature of reality. We do not yet have the language to fully describe what the graviton is. The theory that will give us that language does not exist yet. When it arrives, when the theory of quantum gravity is finally built, it will not just explain a particle, it will rewrite our understanding of what the universe is made of at its most basic level. Every question we have asked in this video was really a single question in disguise. What is reality? At the very bottom. We are still learning to ask it correctly.